Good afternoon. It's Thursday, September the 4th, and thought we'd talk for a few minutes about Chapter 2 of Healey. This is the beginning of the segment that focuses specifically on descriptive statistics. This chapter and Chapter 3 and Chapter 4, central tendency and measures of dispersion, which we'll talk about over the next couple of weeks. You remember from last week when Chapter 1 is almost like a glossary, a lot of bolded terms, essential concepts for getting our minds around as we move through statistics over the course of the semester. And descriptive was one of those, and if you remember, it was comparing it to inferential and all of that. We'll get into inferential later. But descriptive, another way of thinking about descriptive, as it is said in the textbook as well, is it's univariate. It's one variable statistic as opposed to, say, bivariate that looks at the relationship between two variables. Here we're looking at the internal dynamic of a variable, particularly next week in Chapter 3 and Chapter 4. But this is about the internal dynamic. The other thing that's important to remember about statistics, it is a way of summarizing and reducing data down to a single element. And this is an illustration here. A proportion would be an illustration of that. I'll talk about that in a second. So there are three pieces in this video I want to talk about coming out of Chapter 2. One is these terms here: proportion, percentage, ratio, rate, and percent change. And I want to introduce the idea of probability, basic concept about it. And then I want to look at distributions that are frequency distributions for a few minutes. Now those we won't do so much on the whiteboard, maybe a couple of things. And then the third part of the chapter is really about figures such as pie charts, bar charts, histograms, and line charts. And we'll just use some diagrams that we see in the text. I'll probably hold them up or point them out to you. Okay, so here we are, descriptive and univariate. We will be in descriptive and univariate the next 2 or 3 weeks. The internal dynamic. This one is not so much about, it is about internal dynamic, but not quite so much emphasis on that as we'll see in Chapter 3 and 4. Okay, let's take a look at what we got here. Many of these terms will be familiar to you. You've probably heard of proportions and percentages and rates and maybe ratios and things like that. Let's look at how they're similar and how they're different. Here, proportion, you can see here with proportion and percentage, they both have a similar numerator and denominator. The frequency, in other words, the numbers of males, and if we were talking about our class, the numbers of males, and the n would be the numbers of people the total people in our class. Here you can see the percentage is the same thing, but it is a proportion but multiplied times 100 to get the percent. We do proportions in the regular world we live in. We don't see them quite so often or think about as much as we do percentages. So here, let's walk through a proportion. These are data that they're fictitious data. I don't really know how many males there are in our class. But let's say in our class we have 10 males and 30 total in the class. 10 males and 30 total. So the proportion, we divide the total into the 10 males, and we have a proportion of 0.33. Something pretty straightforward. Sometimes proportions are not so easy to interpret. They work well embedded in other mathematical operations, but just to say we have a proportion in class of 0.3, it works, but it doesn't work quite so cleanly as if we were to say percentage, which is the same numerator and denominator, but multiplied times 100, where we got that same value of 0.33 multiplied times 100. We say we have 33% of the students in our class are male. Now that one we identify with because we do think a lot in our culture. We express a lot of these things in terms of percentages. Now, one thing about a probability that's not in Healey at this point, it'll be there later, is just to talk about how it is a proportion, but just expressed differently. So that, for example, here we've got a proportion of 33, and if we look at these decimal points, immediately to the right is the tens, the second is 100. So this would be a proportion of 0.3 or 0.33 out of 100 or 0.3 out of 10. So if we look at that in terms of a probability, then we would say, take this 0.3 and we would say 3 out of every 10 people in the class are male. So then we'd say the probability of encountering a male in our class is 3 out of every 10, because the 3 is in that position of 10. Or we could say 33 out of every 100. Doesn't quite make sense to us because we don't have 100 people in the class. But if we were doing what we were doing last time, where we had that pathway of population to parameter, drawing down to the sample, to the statistic, using that statistical finding to infer what we would have found had we gone from population to parameter. You remember that pathway. Keep that one in mind. If we were doing that here, and we were looking at the proportion in our sample, say our class is a sample, and it was randomly drawn and it's representative of the larger population, all of that. If we found that that proportion is 0.3 in our sample, then we could say, our inference could be that had we gone from population to parameter, we would have found that a proportion similar to 0.33. So then we could say in terms of probability, as we go out into the population, we would expect to find out of every 10 people we encounter, 3 males. 3 males out of every 10. So if we were using it as a statistic in a sample, then we could infer that we would find 3 out of every 10 people we encounter in the population, be roughly 3 males out of every 10. So that's the proportion, it's the probability. This proportion, the percentage, the probability, all of that as a descriptive statistic could be part of our inferential statistic of that estimating the parameter from our statistic. And we'll talk a little bit more about that over the a couple of weeks from now. Now here a ratio has a similar numerator in a way, but the denominator is very different. Here the total is the denominator. Like if it's a class, it's the whole class. If it's a city of San Antonio, then it's all of the city of San Antonio. Here what we're looking at is a ratio between 2 categories of male and female, and we want to know what is the relationship of males to females, not how many males to the class or how many females to the class, but the ratio of males to females. So in this case we've got 10 males, so we're assuming that we've got 20 females in a class of 30. What I usually do is I put the larger value in the numerator, and so divide the males into the females, the 10 males into the 20 females, and then I can get a reading that says that for every there are 2 females for every male. There are 2 females, or for every male there are 2 females. So ratios are another sort of reduction of data into a singular statement. And if we were looking at, say we were comparing our class to another class, maybe in another class it's a ratio of 3 to 1 as opposed to 2 to 1. Or maybe in another class there are more males than females. So that in itself, just a single value like that, is a good descriptor that describes the differences, say, between 2 classes or 2 populations. Reduces the data of 30 students arrayed across the categories of gender, male and female, into a single value. Rate is very similar, you can see here, to proportion and percentage. But here what we do is we divide by or multiply times 1,000, 10,000, or 100,000. Often what happens with the frequencies over the numerators in a rate, the frequencies are so small, like a homicide, 230 homicides in a population of 3 million. The numbers are so small that if we divided the n into that frequency, we'd get a fraction. We'd get a 0.008 or 0.003, something that would be difficult to interpret. So instead of multiplying times 100, as we do traditionally in a percentage, we might multiply times 1,000, or we might multiply times 10,000, or we might multiply times 100,000. And one way to think about which of these to choose is when you take a look at the breakout of however many zeros there are to the right of the decimal point, how many do you multiply times 10,000 to get a whole number on the left, or you multiply times 100,000 to get a whole number on the left? So that basically in this relationship, the larger the denominator, the smaller the frequency at the top, the event, then the larger the k that you will use in terms of multiplication. The other thing that is the essential, really, distinguishing characteristic of rate from proportion, percentage, and probability and ratio is it's enclosed in a time interval. We do rates for 2005 and 2010 and all of that. We don't often think about proportions in terms of time intervals. What was the proportion in 2010 compared to the proportion in 2011? We can do that, but rates are always expressed in terms of years or in terms of time. You could have a rate by day, by hour, by week, by month. So that's a distinguishing characteristic. Now, percent change is a very handy tool. For example, I was just saying here, you'll see the formula in the book where you look at the frequency, say at time 2, and you subtract whatever the frequency was at time 1, and then you take whatever that difference is and divide it by the frequency of time 1, and that gives you the percentage change from time 1 to time 2. Very useful tool to describe a change between these two times. For example, here, homicides 200, homicides 238 over homicides of 200. We get a difference there of 38 divided by 200, and we get a 0.19, multiply it times 100. Then we can say the percent change here was a 19% increase in homicides from time 1 to time 2. A very informative statistic, singularly summarized, reduced down to a value that in a moment tells you a 19% increase in homicides. Whew, there's the story, isn't it? Now you want to go in the background and find out why that happened. Now, of course, if this number were smaller, it's positive because this number is larger than that one. If this number were smaller than that one, say this was 200 and that was 238, then that over there would be a minus 0.119, and then we would say that the percent change is a 19% decrease in homicides. The way we have it set up here on the board, it's a 19% increase in homicides. So these particular descriptive statistics are very, very informative. Reduce data down, numbers of males and females and numbers in class, to a singular feature of that class. Put them in intervals for rates, and then look at comparisons between two times in percentage change. Very powerful descriptors of the data that represent human phenomena, like what we capture with our statistics. Now, I think I'll use the textbook here, and when we're talking about frequency distributions, you'll see that it started on page 31. I'm using here the 8th edition of Healey. Remember, from our level of measurement, we have three kinds of variables of importance to us. And what are those now? Yes? Yes? We have a nominal variable. Nominal variables are things like male, female, Protestant, Catholic, African American, non-Hispanic white, and Hispanic white. There's no numerical scale that differentiates those. There are categorical differentiations that we make. They're nominal. Differences in nombre, nominal. Ordinal, remember, there's an implied scale. Not so happy, happy, very happy, I'm down, I'm up. There's a scale back there. So ordinal variables, those two are categorical variables. It's a categorical distinction between very happy and happy. A categorical distinction between male and female. And then the third variable that we have, level of measurement rather, is interval ratio. These are variables where there is a zero, if you remember from last week. You cannot say, I have no gender, or you cannot say, I have no race and ethnicity, or I have no attitude. People, you can say, you have no attitude. But we always have something there in those variables of nominal and ordinal. But we might be without dollars. $0, 0 children. Interval, remember, is no child plus 1 is 1 child plus 1 is 2 child, where the interval is constant. It increases by 1. But it could be 0, could have no children. Then the more continuous, the ratio is more continuous in terms of dollars and nickels and dimes and pennies and all that sort of thing, using income as an example. So when you're looking at the categorical variables, the way to look at those is you'll see when we're looking at frequency distributions, it's very similar to this. This is a frequency distribution. There are 10 males over out of 30 students. So that frequency distribution of males is a ratio or a proportion of 33 or percentage of 33%. So these often are used to represent the frequency distributions of the categorical variables of nominal and ordinal. if we were to do a little survey in the class and say who's very happy, who's not so happy, and let's say we came back with 10 people who said they're very happy, then we would be getting the frequency distribution by proportion and by percentage of those of us, who are very happy. So take a look at that, and I think that's enough to kind of look at how the frequency distributions are for categorical variables. The continuous interval variables, they're a little more complicated. There's a good illustration of it on page 33. I don't know if you can see this, but take a look at that. What you have here are 50 prisoners working enrolled in a work release program, and the question is, how young or old are they? Well, what you have are 50 ages here, just laid out. They're not in any sequence. If you look closely, you can see a young age of 18 and older age of 75. But, if somebody were to say, is that a young or old group, it would be hard to say. So what you do in something like this is you set up a distribution table, and Healey's got a very good illustration of that here, so take a close look. And the principle here is you take the lowest value and subtract it, which is 18 in this distribution, and subtract it from the highest value, which is 75, and the difference you get is 57, and he's laid it all out here. You divide that by 10, because when we do this, we generally do 10 intervals of distribution. You can see here he's got 10 intervals in this table, and though the first interval, then if you divide 10 into 57, you get a 5.7. You round it up to 6, so that means you want an interval that has 6 values in it. So if we say 18, then we go 18, 19, 20, 21, 22, 23. 23 values in this interval of 6. And so then what you do is you go into this array of data and you find all the values that are between 18 and 23 and put them in that first age interval of 18 to 23. And then you do the same thing for 24 to 29, 30 to 35, 36 to 41, etc., etc. And it's a bit tedious, but he's got it laid out and you can see how it works. And then if you do this, then you'll see after you get down to that group at 30 to 35, you've got 52%. 52% of, look at the percentages here, 52%, sum up those percentages of the first 3 intervals, comes to 52. That means 52% of this group of 50 work release program individuals are under the age of 35. So bingo, you got a descriptor of the age of this group. Half of them are under the age of 35. So that's the value of a table like this. Take a look, and you won't have anything as elaborate as this on homework or on an exam, but you will have the principle of how to calculate a table, set up a table. Take the lowest value from the highest value, divide by 10, and set up these that way. Be sure you got an idea about the process for doing that. All right, so let's take a look at the last piece of this chapter, charts and graphs, section 27. One of the things you want to about when you're doing a stats report or maybe reading statistics, consuming statistics in an article or something, is the visualizations. Text is fun. You can read the text, but the adage that is a picture's worth 1,000 words. If you can show it in an image and then write some text, then you really convey the message that you want to do. And images and graphs and charts, those are other ways of reducing data onto a single value in a sense of image that you can see it. In this case, reducing it to an image. You can write page to page, 2 paragraphs, 15 pages, but nail it in a single image and then write around that. There are images here. There are pie charts and bar charts and histograms and line charts. And what you want to about is when you're doing a report, you want to put yourself in the person who's reading it. There are out there who love text, there are people out there who like images, there are people who like it both. And so then you want to think about, well then probably what I do is have a mix of presentations of my theme. I want to do some text, I want to have some images, maybe a table,
conveying it in any number of different kinds of dimensions and facets, really in order to make the point. And here's an illustration on 43, is a pie chart. What this is, marital status of respondents, married and divorced, that's a variable. Status varies by 3 categories of single, married, and divorced. That's a, what kind of variable? Yes, nominal. Well said. So here then what they've done is they've done the frequency and then the percentage, and they developed a pie chart. Half the pie is still 50%, a third of the pie a little over married at 35, and a piece of the pie is percent divorced. Really quickly you can see the distribution in a visual image. Now you can write a paragraph about that as well. The other thing you want to think about is maybe a pie chart is not the best way to convey. You want to do a bar chart. Here's a bar chart of the same percentages. Here is single, married, and divorced, the marital status, frequency. Maybe you would say, as you look at it, you're in control here. What is the best way to convey the image of what's the best image to convey what I'm going to do? You may decide on pie charts. You may think, well, maybe pie charts are cool in some ways, but also ought to support it with a bar chart also. You might do paper, both bar and pie. Maybe not on the same marital status, but have pie charts for some things and bars for others. Mix it up. Make it interesting. Give them variability in your report that entices the eye. Okay, so I'm over here. The thing you want to keep in mind about bar charts is categorical. Bar charts have space between, indicating that there's no numerical value, nominal, ordinal. There's no scale between them, only apply to an interval. No scale, so that space of bar means it's a category. If you didn't know anything about this, and all you saw were 3 bars, you'd know it's a categorical variable. Just because bar chart. Right. So if we come over here, here's bar chart interest here on this side of the page. You can see that this is sample the chart for this per year retirement. And you can see the frequency of its, and you can see that the 224 is the one most often, followed 50 to 4, followed by 0 to 4. So really quick, you could write a graph about it, but really quick, bar for bar image of that distribution of these. Now down here, it's because you may think, well, maybe I got 2 to do, I want to compare, but maybe by side chart, if you want to put the same chart, simulation here. This is high is here. No circle are the when you are these in your so as you move from clear to they mirror one another. The male homicide rate goes up, and it goes to the female rate. Half, and so even less than half. So in a comparable studies, you can see that $60 to $80 around such a grand very